Welcome to this video about the classic P-Chem experiment of the adiabatic expansion of gases, a very complex history of what is a very simple experiment. The adiabatic expansion of gases is the classic P-Chem experiment where the students will take a container, fill it with a gas under pressure, release the pressure, then put the cap back on the container and watch what happens next. Now, if you've seen my Carnot cycle videos, you know that I am not here to explain the mathematics of this experiment to you, and your P-Chem professor can do that far better than I can ever hope to. But I think you'll find the history of this experiment is really very interesting, and maybe it can give you some insight into why you're doing this experiment and what it's all about. But before we get into the history of the experiment, let's look at a few basic definitions. And the first one is heat capacity. Now, when we're talking about heat capacity, we're talking about how much heat is required to raise the temperature of a certain substance by 1 degree. And this calculation can be done for gases, liquids, or solids. Now, when we're thinking about a gas, we are usually thinking about the molar heat capacity, which is defined as the amount of heat required to increase the temperature of 1 mole of gas by 1 degree Kelvin. Now, there are two ways we can think about this molar heat capacity: the measurement at a constant pressure and the measurement at a constant volume. So let's consider the constant volume first. We've got a container, it is sealed, there's a gas inside, and the volume of this container is fixed. Now, what happens if we put some energy into this container, or if we try heating it up? Well, as we heat up this container at a constant volume, the pressure is going to go up, but all of the heat that we put into this, or all of the energy that we put into this container, is going to increase the pressure. Now, let's consider an alternative where we're going to work at a constant pressure. We've got the same or similar container, we've got the same gas inside, and now instead of a fixed volume, we've got a moving piston so that the volume can change as the gas expands. So now we are putting energy into this gas. The gas is expanding, the pressure remains the same, but because the volume is expanding, the expanding gas is pushing against this piston, and this piston has to push against the air pressure, which is pushing it back. That's why we say it is at constant pressure, because the air is pushing back on this. The thing is that some of the energy we put into this gas went toward increasing its temperature, and some of the energy we put into this gas went into doing the work of increasing its volume. So the heat capacity at some constant pressure is always going to be different from the heat capacity at some constant volume, because when heat is added at that constant pressure, the substance expands and does work. Okay, this is a spoiler. I'm going to talk a lot about the speed of sound in air. And if we look at this nice slide from the National Aeronautics and Space Administration, we see that the speed of sound in air is the square root of the temperature of the air in Kelvin, the universal gas constant, and the ratio of the specific heat, or the ratio of the heat capacity between air at constant pressure and the heat capacity of air at constant volume. Okay, sorry about the spoiler. Let's get back to the adiabatic expansion of gases. Our story really begins in 1627, when Sir Francis Bacon first observed that if you set off an explosion The light from the explosion reaches an observer just about simultaneously, but the sound from the explosion reaches the observer a few minutes later. So he proposed to measure the speed of sound in air by setting off an explosion on a distant hilltop, starting a timer, and stopping the timer when the sound reached the observer. And this experiment was performed by the Florentine Academy a few years later. Now, if we're going to measure the heat capacity of something, obviously we have to have some kind of a thermometer and some kind of a temperature scale. So in 1681, Robert Hooke, the English scientist, was the first one to propose a temperature scale based on the freezing point of water and the boiling point of water. The Fahrenheit temperature scale, which many of us will be familiar with, really was introduced in 1714. Now, Sir Isaac Newton in 1687 measured the speed of sound in air, and all he did was clap his hands. A sound wave traveled through the air, hit a brick wall, bounced back, and he heard the sound wave. So what Newton had to do was figure out or measure how far he had to stand from this wall so that the sound left his clapping hands, hit the wall, bounced off, and hit his ears. And if he knew the distance he was standing when that round trip took exactly 1 second, he would have the speed of sound in air. Now, it's a very, very simple experiment, and if you have a handy brick wall, you can do this experiment yourself. But if you're taking P-Chem, you know that there is nothing, absolutely nothing, so simple that a chemist cannot make it more complicated. And so the first thing that Newton did was trying to calculate a theoretical value for the speed of sound. He had measured it, he knew the actual value, now he wanted to calculate a theoretical value and see if these two numbers would match. So he got a theoretical value for the speed of sound in air between 920 and 1,085 feet per second. In his second edition of the Principia, he amended this value to 979 feet per second. But he knew that this value was about 20% low because the measured value of sound in air was 1,100 feet per second. Euler came along and he performed similar calculations that accounted for air temperature. And now he got a value between 1,069 and 1,222 feet per second, which was much closer, of course, to the 1,100 feet per second that was actually measured by Newton. So we had a bit of a crisis in science because Newton had made an error. Oh my goodness. Now, if the world's greatest physicist could be 20% off, everybody knew about it, and this was very, very embarrassing. So what did Newton do that gave him the wrong number? Well, it was actually what he did not do. At this moment in history, the 1680s, people knew that sound was the transmission of a wave through the air. Now, Newton, of course, was working well before the atomic theory, but he thought that the air consisted of air particles. Now, you have an air particle with a certain diameter, and you have the distance between two air particles at some multiple of that diameter. So now you're going to have a sound wave travel through the air. The speed of the sound wave will be determined by how fast a particle covers that distance between itself and the next particle. If it's able to transfer its energy to that second particle, which will then cover the interparticle distance in a certain amount of time, strike a third particle, transfer its energy to that third particle, which will then cover that interparticle distance, strike a fourth particle, and so on and so on and so forth. And basically, he thought that the elasticity of the air, the ability of the air to transfer those particles, or the ability of those air particles to transfer their energy, was simply a function of sound intensity. So if you made a more intense or louder sound, you had a better transfer of energy through the air particles. Now, what Newton did not do was account for the temperature of the air or the pressure of the air. And that's where he made his mistake. He did not account for the temperature of the air, and he did not account for the pressure of the air. Now, wait a minute. I hope you're thinking to yourself, air, a gas, temperature, pressure. Hey, wait a minute. This all has to do with the universal gas law. This all has to do with Boyle's law, right? All right, before I answer that question, let's talk about the discovery of the adiabatic heating and cooling of gases by William Cullen of Scotland. And in 1755 and 1756, it was noticed that if you compress the gas very, very rapidly, you would get a temperature rise. And if you allowed a gas to expand very, very rapidly, you'd get the temperature fall. And the gas would get hot, and the gas would cool off without the transfer of heat from the surrounding environment. In other words, it would do it adiabatically. So by 1779, adiabatic heating and cooling were now being discussed in the chemical literature, and by the mid-1780s, value for specific heat were being published. Now, it's very easy to calculate the heat capacity ratio. You took a gas at a constant volume, you added a known amount of heat, you had a known increase in pressure, that gave you your heat capacity. Or you took a gas at a constant pressure, you added a known amount of heat, you got the heat capacity that way, you took the amounts of heat, you divided the two, and you'd get a heat capacity ratio. It is a fairly simple calculation. So I'm going to let you think about that for a moment while I pause this video and resume with my next slide on part 2.